Okay, prime factorization. The first thing that is important that you understand in prime factorization are the differences in some vocabulary words. Okay, the first one is multiple. A multiple of a number is the product of that number and any non-zero whole number. The least common multiple of two or more numbers is the smallest multiple that is common to all the numbers. Okay, so multiples are your times tables. So for example, down here it says, well, let's look at this one where it says the least common multiple of 3 and 4 is 12. So if I were to list out multiples of 3, that's 3, 6, 9, 12, 15, 18, 21. We could go on and on and on forever and ever and ever. Multiples of 4 are 4, 8, 12, 16. Okay, and y'all will notice I stopped because I got to the first one they have in common. The least one is 12. So that's what the least common multiple is. It's the smallest multiple that they both have in common. So look at number 1. Computers are delivered to a store every 6 days and printers are delivered every 9 days. If both printers and computers are delivered today, when will they both be delivered again, like at the same time? Okay, so computers are day 6, day 12, day 18, 24, 30, 36, on and on and on. Okay, and printers are day 9, day 18. Whoa, why can I stop right there? Because this is the same. That's the first multiple that they have in common. And then last week we worked on our divisibility rules, and those will come in handy because, for example, if I'm looking for a multiple of 4 and 10, okay, I can list out my multiples of 4, and then I know that if it's going to be divisible by 10, it has to end in a 0. So tell me when we get to one that stops in a 0. 4, 8, 12, 16, 20. Right? I'm stopping there because I know they're both divisible by 20 or by 10, and that's the first one. Okay, same thing here. I don't know, or I don't have a rule for 7, so I can go ahead and list out multiples of 7, and I'm going to stop when I get to one that ends in a 5 or a 0, because then I know it's divisible by 5. So 7, 14, 21, 28, 35. And I stopped because if I'm listing out multiples of 5, 5, 10, 15, 20, 25, 30, 35. And I'm done. Okay, so let's look at multiples of 12 and 15. If it's going to be divisible by 15, it has to be divisible by 5 or end in a 5 or a 0. 12, 24, 36, 48, 60. And I stopped because 15, 15, 30, 45, 60. Okay, and multiples are different than factors. Factors are the numbers that you multiply together to get a number. So for example, factors of 30. Those are numbers, like what pairs of numbers can I multiply to get 30? Well, I could do 1 times 30, and I'll explain why I'm writing them so far apart. I can do 2 times 15. I could do 3 times 10. Is it divisible by 4? No. Is it divisible by 5? 5 times 6. So by writing it like that, my numbers ended up in order from least to greatest, which is what I wanted. Okay, so now find the factors of 42. 1 and 42, 2 and 21, 3 and 14. Is it divisible by 4? Nope. 5? No. 6 and 7. So those are factors of 42. Okay, it's what can you put together, what can you multiply together to make that number. Okay, so composite number is a whole number greater than one that has more than 2 factors. And a prime number is a whole number with exactly 2. So if you were to look at the number 7, the only things that you can multiply together to get 7 are 1 times 7. So it's prime. For 14, I could do 1 times 14 or 2 times 7. So it's composite. 12, composite, because you can do 3 times 4. 15, composite, because you can do 3 times 5. 13, prime. It's only 1 times 13. 11, prime, only 2 factors, 1 and 11. 2, prime. 63, composite. This is where those little checks that we learned last week come in so handy, because you might not be sure, but 6 plus 3 is 9. So, oh yeah, that's divisible by 9, and it's divisible by 3. Okay, the next thing we're going to do is prime factorization. In prime factorization, I like to use factor trees, and so here's how you do it. You start with your number, and then we're going to write what it's divisible by. So what can I multiply together to make 60? Well, I could do 6 times 10. What can I multiply together to get 6? 2 and 3. Okay, 2 and 3 are both prime numbers, right? There's nothing I can multiply to make 2 other than 1 and 2. So I circle those. What about 10? What can I multiply together to make 10? 2 times 5. So now when I go to write the prime factorization, I start with our smallest prime number, which in this case is 2. I have 2 of those, so it's 2 squared times 3 times 5. We're going to do the same thing for 72. I could say, well, that's 8 times 9. 8 is 4 times 2. 2 is prime. 4 is 2 times 2. And those 2's are prime. And then 9 is 3 times 3. So what did I do? What prime numbers did I multiply together? I have 2 to the third power times 3 to the second, because there's 3 2's and 2 3's. That is hard to say. Okay, let's look at 36. Actually, why don't you do it on your own paper? Okay, so pause the video and then come back and we'll see if your answer matches mine. Okay, I'm going to say that 36 is 4 times 9. 4 is 2 times 2. And 9 is 3 times 3. So that gives me 2 squared times 3 squared. And it doesn't matter if you picked 4 or 9, or if you picked 2 and 18, or 3 and 12, okay, you're always going to end up with the exact same prime factorization. So turn your paper over and let's talk about greatest common factor. So now that we know what factors are, right, the factors are the numbers that you can multiply together to get the number, right? It's essentially what it's divisible by. There's 2 methods of finding the greatest common factor in a set of numbers, and the first is by making a list. So for 24, we're going to list out all the factors of 24. You can do 1 times 24, 2 times 12, 3 times 8, 4 times 6. Okay, and this should actually read 36, not 26. Factors of 36 are 1 and 36, 2 times 18, 3 times 12, 4 times 9, and then 6 times 6. You can just list it out one time. So we are looking for the greatest common factor. Okay, not the least, because that would be 1 for every single set. It's 12. That's the biggest number that is a factor for both of those. Okay, but the list is kind of a pain because it's a little bit tedious, and what if you forget a number, that kind of thing. If you forget a factor, it can throw you off. So we can also use factor trees to determine a GCF. So let's set this up for 24. I'm going to say 6 and 4. 6 is 3 and 2. 4 is 2 and 2. Okay, and then for 36, I'm going to say it's 6 times 6, 2 times 3 for each of those. So now what we're going to do is we are going to essentially like pick our prime fruit off of our tree. But we have to pick the same fruit off of both. So for example, I could say, well, I'm going to pick this 2 because there's a 2 here and a 2 here. So I write down what I picked. What else can I pick? What's the same? Well, they both have another 2, right? I can pick a 2 off both the trees again. And then what else can I pick off both the trees? A 3. So they both have 2 2s and a 3. 2 times 2 is 4. 2 times 2 is 4. 4 times 3 is 12. So that's my GCF. That's the exact same answer as up here. So now we're going to practice it. Okay, it says find the GCF of 40 and 32. So I'm going to set up my factor tree for 40. That is 2 times 20, which is 2 times 10, which is 2 times 5. And then for 32, that's 2 times 16, which is 2 times 8, which is 2 times 4, which is 2 times 2. So now what I do is I come in here and I'm like, okay, well, what can I pick off both of the trees? They both have a 2. They both have another 2. They both have another 2. Is that all they have in common? Yes. 2 times 2 is 4 times 2 is 8. So that is my GCF. Okay, and then on this one, it says a synchronized swimming competition requires performers to line up in rows of equal length. What is the longest row for teams of 36 and 60? So 36, 60. Okay, 36 is 4 times 9. 4 is 2 times 2. And 9 is 3 times 3. And then 60 is 6 times 10. 2 times 3, 2 times 5. So when I'm looking for what can I pick off both of these prime factor trees, they both have a 2, they both have another 2, and they both have a 3. 2 times 2 is 4, 4 times 3 is 12. So the GCF of 36 and 60 would be 12.